Today we will start a very new chapter of 12th class, that is electromagnetic waves. The chapter has very advanced role in the 12th class physics, and later on we will find its applications. So start from electromagnetic waves. First of all, writing down the title: electromagnetic electromagnetic waves. So Oersted experimentally predicted that the electric current produces a magnetic field. Faraday from his experiments on electromagnetic induction found that a changing magnetic field produces an electric field. So according to Faraday, found that a changing magnetic field produces an electric field. So according to this, he also predicted that changing electric field can also produce magnetic field. And he predicted that its reverse is also possible. That means changing electric field produce magnetic field. This answer was given by a Clerk Maxwell. What he stated that the magnetic field is not only produced by electric current but also by a time-varying electric field also. Maxwell concluded that his idea on the basis of his experiment when he was finding the magnetic field at a point outside and inside a capacitor connected to a time-varying current using Ampere's circulating law, he found that the results were not consistent. On this basis, Maxwell pointed out that Ampere's circular law becomes consistent only if, along with conduction current, there is an additional current called by him the displacement current. Next, Maxwell formulated a set of equations involving electric and magnetic field and their sources. The charge and the current, these equations are known as Maxwell equations. So we will study next Maxwell equations. These are the set of equations involving electric and magnetic field and their sources, that is charge and current, that is charge and current. These equations are known as Maxwell equations. These equations along with Lorentz-Force formula explain mathematically all the basic laws of electromagnetism. Now Maxwell through his equations came out with a most important prediction, that means the existence of electromagnetic waves which can propagate in space with a speed very close to the speed of light, that is 10 to 10 to the power 8 meter per second. This led Maxwell to conclude that light is an electromagnetic wave. In 1885, Hertz demonstrated experimentally the existence of electromagnetic waves. Later on, Marconi used these waves in establishment of communication between two locations at a distance of about 50 km without using the wires between the two locations. This led to the discovery of wireless communication, and Marconi was considered as the father of wireless communication. Nowadays, the wireless communication has revolutionized our life. So go for the displacement current first of all. According to Ampere's circular law, the line integral of magnetic field the line integral of around any closed path is equal to mu naught times the total current threading the closed path will be this will be question 1, where I is the net current threading the surface bounded by a closed path. C. Maxwell in 1864 argued that the relation in equation 1 is logically inconsistent. He explained the same with the help of following observations. What he considered, let us find the magnetic field at point R, which is at the perpendicular direction or distance R from a consecutive wire in a region outside the parallel plate capacitor. On the basis of this experiment, he concluded that suppose I current is flowing through this circuit, and this will be closed. Then this will be the radius of this wave. So suppose this will be the C1 R, this is plate P, this is plate Q of capacitor. Okay. Consider parallel plate capacitor having plates P and Q connected to a battery B. This is K. Through trapping key, when the key is pressed, the conduction current flows through a connecting wires. The capacitor starts storing charge. As the charge on a capacitor grows, the conduction current in the wire start flowing. As the charge on the capacitor grows, the conduction current in the wire decreases. When the capacitor is fully charged, the conduction current stops flowing in the wires. During charging of capacitor, there is no conduction current between the plates of capacitor. During charging later an instance, I be the conduction current in the wires. This current will produce magnetic field around the wires, which can be detected by using a compass needle also. Now let us find the magnetic field at point R, which is at the perpendicular distance R from connecting wire. In a region outside the parallel plate capacitor, for this we consider a plain circular loop C1 of radius R, whose center lies on the wire and its plane is perpendicular to the direction of current carrying wire, as shown in figure 1a. Okay. The magnitude of the magnetic field is same at all points on the loop and is acting tangentially along the circumference of the loop. If B is the magnitude of magnetic field at R, then using Ampere's circuital law for loop C1, what we have? We have closed integration from C1 to B dot dl is equal to closed integration of C1 B dl cos 0. It equals to B 2 pi R is equal to mu naught I. Or in other words, what we can say? We can say or B is equal to mu naught I upon 2 pi R. This will be equation 2. Now, what we can do? We can add it over figure 1, and this, after a complete charging, the current I flows in a wire will no longer flowing in it, as the capacitor is fully charged. So, having the same polarity, plate P is positively charged and Q is negatively charged. And this time, it is fully charged. Current I is flowing again in the same way. Now, this radiance becomes somehow larger this and on this area. Okay, having the place R. Now we consider a different surface, that means a tiffin box shaped surface without lid with its circular ring which has the same boundary as that of loop C1. The box does not touch to the connecting wires on plate P of capacitor. The plate circular bottom as of the tiffin box lies in between the capacitor plates as shown in figure 1b. Figure 1b. No conduction current is passing through the tipping box surface S. Therefore, I equals to 0. On applying Ampere's circuital law to loop C1 of tiffin box surface, we have, on applying Ampere's circuital law on figure 1b, what we have? We have C B dot dl is equal to B2 pi r is equal to mu naught into 0 is equal to 0. This time B will be 0. From equation 2 and 3, we noted that there is a magnetic field at R calculated through one way and no magnetic field at R calculated through another way. Since there is contradictions arise from the use of Ampere's circuital law, hence Ampere's circuital law is logically inconsistent. Maxwell argued that the above inconsistency of Ampere's circuital law must be due to something missing. Now what is missing? The missing term must be such that one gets the same magnetic field with whatsoever surface is used. This missing term must be related with a changing electric field which passes through the surface S between the plates of capacitor during charging. If at the given instant of time Q is a charge on the plate of capacitor A, if at given instant of time if at the given instant of time Q is the charge on the plate of capacitor, Q is the charge on the plate of capacitor and A is the plate area and A is the plate area A of the capacitor, then the magnitude of electric field between the magnitude of electric field between the plates of capacitor is E is equal to Q upon epsilon naught A. The field is perpendicular to surfaces. This field is perpendicular to the surfaces. It has the same magnitude over the area A of the capacitor plates and becomes 0 outside the capacitor. So the electric flux to the surface S is through the surface S is E dot A, or this will be EA cos 0 degree, and this will be equal to, after putting the values of E, epsilon naught A Q upon A into A, cancel out A, and this will be Q upon epsilon naught. So this will be the value of 5. So this becomes our equation 4. Now if dq upon dt, if dq upon dt is the change rate of change of charge, rate of change of charge with time on plate of the capacitor, with time on the plate of, then d phi dt is equals to d by dt q upon epsilon naught is equal to 1 upon epsilon naught dq upon dt, or we can write epsilon naught d phi dt dq upon dt. Here dq upon dt is equal to current through the, here dq upon dt is equal to current through surface S corresponding to changing electric field, corresponding to changing field is equal to ID, which called Maxwell displacement current. So what is the displacement current? It is the current, that current which comes into play, in the region in which, in the region in which the electric field, in which the electric field and the electric flux and the electric flux is changing with time. So the displacement current is given by, so the displacement current is given by ID is equal to epsilon naught. This displacement current is the missing term in Ampere's circuital law. Maxwell pointed out for the consistency of Ampere's circuital law, there must be displacement current. ID is equal to epsilon naught d phi by dt along with the conduction current I in the closed loop. So in the closed loop, I plus ID must be present and has the property of continuity, although individually they may not be continuous. Maxwell modified Ampere's circuital law in order to make the same logical consistency. He stated Ampere's circuital law to the form phi v dot dl is equal to mu naught I plus ID is equal to mu naught I plus epsilon naught d phi dt. This is called Ampere's Maxwell's law. Ampere Maxwell's law. That's it. Next class or next we will get the continuity of current. Okay.